Let me share my presentation. Okay, so recording also has started. Thanks. Uh, Fine. So in the last class, we stopped here. We were discussing about the inductive learning and the uh, basic statement of inductive learning or characterization of inductive learning is just expressed in this particular uh, you know, this particular mathematical uh, statement. What it says, let us understand. It says that you have the domain of training examples. So D is the set of training examples. Okay, you have the set of training examples, and consider uh, all element in this set or any element in that set. Now, if you find out some hypothesis H, which is closely approximating the target function. So in our example, of course, what we are discussing exact um, exact mimicking of target function of those input samples, but in general, it should be approximate matching of the target function for only those input samples, because those are observable. So if you can get an hypothesis which matches with the output of the target function, what is being specified under the supervised learning framework, then for any sample in that domain, where which also includes the unobserved samples or unseen samples, right? So any sample in that particular domain, or we say population distribution, that is also the similar word. There also this should be true. That means that hypothesis should largely approximate the target function. So this is the hypothesis of inductive learning, and based on which only we are going ahead with finding out a hypothesis which should largely approximate the target function within the training samples. Okay, so that is the motivation when you are learning this particular thing. Okay, so uh, let us again try to understand that what is meant by this hypothesis. I mean, when we say that a hypothesis is approximating a target function uh, given the input samples in that input domain, so how many possible hypotheses could be there which has the similar property? So as I already discussed in the last class, that it is not unique, because your um, training samples, what you are observing, that is a partial observation. So naturally, if it is unique, so that could have been the target function. So that is not true. So there could be various possibilities, and out of those possibilities, one of them is the target function. That is the kind of your premise. So, but what we could see that there is certain kind of ordering among these hypotheses, which are all satisfying the conditions of the target functions in those training data sets. So let us understand that part. With respect to our example and the form of the hypothesis that we have considered, you can see that in this case, say this is a hypothesis. Okay, sorry, this is a data. I'm sorry, this is a data. This is the input space, and these are the hypotheses. These are the hypotheses. So this is a hypothesis. Now, if I get this data, say x1 and x2. Suppose x1 is there, x2 is there. So suppose this, I mean, it's just figurative no, way of showing certain points in the input space. Naturally, it's a 6-dimensional space. The dimensions are also attributes. So it's basically a kind of sketch by which you are trying to show that kind of input space where there are certain points in that input space. Now, if I consider this hypothesis, say H1, we would see that here you can see that suppose these are the sets which are satisfying H1, say, which includes also X1, right? Say sunny, warm, high, strong, cool, same. I understand that you hope you can. I hope you have understood that why it is satisfying, because it is matching with these places, these literal places, right? These equality conditions are satisfying. I mean, this Boolean condition is satisfying that attribute values are sunny and strong for this hypothesis, and these are the don't care stay. So this actually satisfies H1. What about X2? Is it satisfying? Can you tell me? This H1, X.
No, sir.
No, sir.
Where it is getting no?
So
The
the
light.
light is strong.
Yeah. So this is the value at that attribute space, attribute no variable, that light, but here it has to be strong. So that is why H1 does not satisfy X2. What about this one, H2?
It satisfied both.
Yes, sir.
Like H2 satisfies both X1 and X2. So in that case, you can see that if I consider this particular data set X1, okay, so at least whatever if my training example consists of X1 only, so naturally H1 could be an hypothesis. But if my training example is X2 or H1 or H2, both of them could be a possible hypothesis for X1. Okay, but if I consider X2 in the training example, then H1 is not the no hypothesis given that training example that would satisfy all the training examples. So that's why it is not a valid hypothesis given this training example, mimicking the target functions. Valid in the sense that it is not the hypothesis considered to be a target function. But H2, it satisfies both. So H2 is a target function. I mean, H2 can be a candidate. What about H3? Do you have any idea how
X1.
it satisfies?
X1.
It satisfies X1, right? But it does not satisfy the X2. Okay. So there is a certain kind of given this if I say given this hypothesis H1, H2, and H3, you will see that your input data set, if I consider there is in the input space, rather the input space, whatever data, whatever input data which are satisfied by H2, right? Sorry, whatever input data which are satisfied by H1, all of them are also satisfied by H2, isn't it? Any input X which is satisfied by H1 is also satisfied by H2. Is my statement correct?
Yes, sir.
Right? Similarly,
Yes, sir.
any, yeah, please.
No, yes, sir. Yes, sir. Yes.
Okay. And any X or any input which is satisfying H3, that is also satisfied by H2. But not by, we cannot say that thing for H1 and H3, right? But this statement is also true that any X which is satisfied by H3, that is also satisfied by H2. So we say H2 is a more general hypothesis with respect to H3, or H2 is more general hypothesis with respect to H1. Or in other way, we can say H1 is a specific hypothesis with respect to H2, or H3 is a specific hypothesis with respect to H2. So if you look at this particular structure, I mean, or relational, that relation we are representing in the form of a graph here, we can see that a hypothesis is a node here, right? And actually we say this structure is a lattice structure also in the discrete structures. But now here for the understanding, you can see that we have shown that this relationship. So H1 is a H2 is more general hypothesis with respect to H2. So this is shown by this kind of directly, or H1 is a specific hypothesis with respect to H2. Similarly, H3 is a specific hypothesis with respect to H2. But H1 and H3, they are not comparable. Cannot say draw this kind of relationship. So they don't have any relationship with this specific and or general considerations. So in a hypothesis space, all hypotheses, if I consider these are now points in the hypothesis space, like hypothesis space is also a 6-dimensional, as you can see, is a 6-dimensional representation, and they can be also considered as a point in that space. So in the hypothesis space, there is certain kind of ordering that can be observed. And here, so it is nothing to do with training examples, right? It is independent of a given training example. It is simply considerations of the form of the hypothesis, and also the hypothesis is defined over an input space. So considering that, considering the input space and the hypothesis space, these relationships can be observed, and this ordering can be observed. So this has this shows you that given certain training examples, there would be certain set of hypotheses in this space which will be satisfying all the examples, which means which will be candidates of possible target function. We call that set as a version space. That's the name. I will come to that. We call it a version space. So it will be a candidate for the version space. Right? But in the version space also, there is an ordering. That means there will be certain hypotheses which will be more specific than some of their hypotheses, or which will be more general than some of their hypotheses in the versions. But all of them are satisfying the conditions given by the training examples. I hope it is clear.
So I have a doubt.
Right.
So as you mentioned in the hypothesis space, like H1 and H3 are specifics over H2, right?
Pardon? Can you tell me once again your question?
In the hypothesis space, H1 and H3 are specifics over H2.
H1 and H3 are specific. Because of that, no, I told you the
yes.
If you look at
yes.
yeah.
So in the same graph, it is shown that H2 is specific over the bottom 2 points.
No,
so
those are
just
figurative.
Those are
figurative.
Okay.
Those are figurative. I mean, it shows that there may exist hypotheses which are also general than H2 in the same way.
Got it. But in this case, H2 is not in this space. Right?
There is no hypothesis has been cited here where H2 it is more general than H2 in the lists. But you can find out some lists. For example, if you consider all don't care. If you consider all don't care, it is general to any hypothesis in that space.
Yes. Okay.
If you consider all null, it is specific to all hypotheses. That condition. So anyway, so we will come to those properties also. So that is the general to every hypothesis, and the specific to every hypothesis there exists hypothesis in that way, representation. Right. So this is the definition of more general that I was mentioning, and you can note certain kind of notation we are using here, that H is more general than H prime, which means H2 is an example of H here, and H1 is an example of H prime, or H2 is an example of H, and H3 is an example of H prime, right? So if it is more general, if for each instance X, H prime X equals 1, means that Hx equals 1. So that means if a input satisfied by an hypothesis, a specific hypothesis H prime, it should be also satisfied by its more general hypothesis by X. So we did not utter the term specific because it is not required. We say that more general, but the reverse, these relationships, the other way you can say that then H prime is also more specific than H. So this is the question I have already answered, which is the most general and most specific hypothesis. Okay, so is it clear? Can you tell me once again that which is the most general hypothesis, considering all hypotheses in the hypothesis space?
H2.
H2.
No. This is I'm not considering this
It will
example.
be all don't.
Okay.
All don't
The
care.
case
All
with
don't
all
care.
don't care.
Yes, it is all don't care. Tuple. Huh? So any hypothesis will be more specific to that. And similarly, which is more specific, most specific hypothesis? This is all null. All null is the condition. So finally, as you can see that your learning can be considered as a searching problem over the hypothesis space. That means if you give you a set of training examples, you have to find out. You can enumerate possible hypothesis in the hypothesis space. If I say in an exhaustive manner, in a brute force manner, you can consider every possible candidate in the hypothesis, every possible point in the hypothesis space, or every element in the hypothesis space, and just check whether your input samples, training examples are satisfied by that hypothesis. Then you say that is a kind of your candidate hypothesis, or it's an element of version space, as I mentioned. But out of them again, you need to consider that now which is general, etc. Because we will be coming to that also, why it is required. This is one thing. I mean, you should understand that computationally it has become a kind of a search problem. And as I just mentioned that if examples are error free, then H should satisfy all of them, which is presently we are considering that situation. But naturally, it is not unique. We have seen that, and there are several alternatives are there. It may not exist any solution at all. Yes, there could be training examples where there may not be any hypothesis fitting with it. It is not that set of training example is erroneous, right? Training examples may be, I mean, there may not be any error. Can you tell me with respect to this problem? Can you give an example, or can you just describe a situation where you will not find any hypothesis in the hypothesis space which will match the training example? Can you explain? Any one of you?
So when all the elements of the training examples are different, that's it.
What do you mean by different? I mean, as such, no. In the training example, if I say all the elements are different, actually all the elements are to be different.
So I mean to say in a particular set, in every particular set, all are different.
That would be also there. I mean, otherwise there will be contradiction. So then there will be an error. Say if I say certain tuple of input, your functional value is 1, and then in another case we say the functional value is 0, there is a contradiction. So that is an erroneous condition. That should not be there. So it has to be distinct. All examples are to be distinct.
So where we are saying that there does not exist any solution at all, isn't the null hypothesis considered as a hypothesis?
It means that no, there are certain kind of Boolean expressions which would be satisfied by the training examples, but no, your formation of your hypothesis, that assumption or that structure is not capable of expressing them. So you will not get them as a point in your hypothesis space. I have given you enough hint. I think you should be able to tell me now.
Sir,
I told, yeah, please.
can you go to the previous slide?
This slide will not help you. I'm just going, I'm taking you.
Sir,
yeah.
Sir, if I take two example, means the x1 and the another one means there will be this x1 which will be sunny, warm, high, strong, cool, same, and another will be the instead of sunny there will be something else. No, it will be like it will be and something which is opposite, not sunny, means two a value of two attributes will be changed.
So why then it is not admissible? See, in this case we have listed only positive examples. We can what is not this is not exactly 10 examples here. I have given you only the input data set and saying that whether they are satisfied or not, means positive. So, but I should say, I should give you another information with this. When I say this is a training example, I should say whether the level is positive or negative, okay? Or
Yes,
1 or 0 or yes or no. Then it becomes a training example. Then it is a training example. So, as such, this information was incomplete, but we have assumed that no, they are all positive examples. Right. With respect to that, can you tell me once again?
Yes, sir. Sir, actually, I have forgot the values name against.
Yeah,
the
there are values like no. You for example, for sky, there are 3 values: sunny, then cloudy, right, and then rainy. Okay, I'm just writing in a short form.
So, sir, there will be one example of x1, and there will be another example like cloudy, and there will be something else instead of warm. The second
instead of warm.
Yes.
You are saying another attribute.
Another value means
no, but warm means so this is another. I think this is temperature. It should be
yes,
warm
yes.
or cool or something. Huh?
Yeah. It will be cool.
Cool. So how does it now? Why it should not admit an hypothesis? Because if I say these are all positive examples, you are saying.
And sir, I will again put some negative example which will not
you
be.
Put some negative examples. But fine, you put some negative examples. So why should you say that your hypothesis space does not have any hypothesis which will satisfy them?
Sir, here we have changed the values of two attributes. So how can we generalize it to fit all the positive examples, and how can we ensure like if something negative value comes means to make these two attributes don't care, and if something negative value occurs there, so like we can do this by first two attributes will be don't care.
See, whether there is enough. Suppose what you are saying, I will put say this is instead of sunny, let me write it as cloudy. Okay, this is the positive example, and say next example I will say this is cool, right?
Yes, sir.
And rest other remains same, and I will say this is negative example. But I can always,
No, sir. This will be positive example.
This is positive example.
Yes.
So this most general hypothesis itself will satisfy.
And I will, sir, if we put sunny, then cool, then rest of the things same, and keep it as a negative example.
Yeah, sunny, cool, and rest of the things same, and keep it as a negative example. Then what happens that you are putting here constraint on warm, right? So we can put warm only, and put all don't care.
Okay, and again, if we put some cloudy and then cool and then negative.
That is okay. So you put constraint on this only. You put constraint on sunny and cloudy. So since this is cool, so it doesn't matter. I mean, you just put sunny and you can put question mark here, warm and all question mark. Similarly, cloudy and here warm and all question mark. So the question is that, sorry, not since it is sunny, you can put question mark, warm and all these things, and question mark, cool and all the yeah. I mean depends upon, but it is not that case. It will not be. There should not be any hypothesis. I mean that does not give. So you tell me what you're saying. I will give you an example. So this is cloudy. You're saying cloudy, cool, and this is negative example. That is what you are saying.
Yes, sir. The sunny, cool, that is the negative example, and
sunny, cool, that is the negative example. Okay.
And again cloudy, cool, that is no. Yeah. Sunny, cool, and sunny, cool, and cloudy, warm is the negative example.
No, see, sunny and cloudy you cannot put together, na? Either sunny or cloudy.
Okay. Yes, sunny, cool, that is one negative example, and another is cloudy, warm, that is one negative example.
Another is cloudy,
warm.
Cloudy, warm.
Warm.
Yeah. Another is negative example.
Yes.
Which means that you can put sunny and then warm, right?
Yes.
Then warm and all don't care state. Okay.
Yes.
And then you can put. Is it cloudy? Is it also cloudy? You can put cloudy and warm and all don't care state.
So,
that also.
The cloudy, warm is negative, right?
Which one?
Cloudy, warm is negative.
So then don't put it.
Okay.
Then
and another is that cloudy, cool is
Pardon?
positive. Cloudy, cool is positive.
Cloudy, cool is positive. Okay. So which means that you can put then, you can put question mark, right?
Yes.
Warm. Yeah, actually, you are saying two attributes. Just a minute. So question mark, warm, all positive examples, which means no, you are saying sunny here, no?
Yes.
Sunny. Yeah. So there lies one contradiction. So okay, you can have sunny, warm, all question mark, and then you are saying cloudy and
cool.
Warm. Sorry, I just forgot. Cloudy, cool.
Yes, sir.
But cloudy, warm is acceptable, you are saying, no?
No, sir. Cloudy, warm is negative. Cloudy, cool is positive, and sunny, cool is negative. I told it positive and two negative.
Sorry, just let me take two only. Sunny, warm is positive.
And the cloudy, cool is positive.
Cloudy, cool is positive.
And the other combination means sunny, cool is negative, and cloudy, warm is negative.
Sunny, cool is negative, and
cloudy, warm is negative.
Cloudy, warm is negative.
Excuse me,
so,
sir.
Yeah.
So how is cloudy, cool positive? It is not given in the question, right?
No, he is assuming. This is possibility, no? See, you are labeling them. So these are the possible levels. So sunny, warm is positive. Pardon?
But we will label according to the training examples, right?
No. See, this is your training example. See, these are assumptions. You are forming your training examples. So you are trying to get an hypothetical situation, whether you do not have any hypothesis which will be satisfying these conditions, right? So yes, I think this is what you are saying, that sunny worm is positive, but which means that I'm writing it in the form of yeah, I think there you are correct. So when the Boolean expression, so if I write it in the form of Boolean expression, I will be writing it as sunny worm, then you say cloudy, both cloudy and cool, and so these are the things you will be writing, isn't it? Sunny worm, cloudy, cool. Now here একটু পরে কথা বলছি।
So in the training examples, we are just given x1 and x2, right? And we have to form the hypothesis.
No, that's okay. So I'm just considering here x1, x2, x3, x4 in two-dimensional space. You take this. See, these are two-dimensional space. So sunny worm, yeah. So in this case, we can write either sunny worm, or can I write something like this? Yes. So there does not exist any hypothesis which will satisfy both the things, as you say in these conditions. All the training examples. Either I can write sunny worm, or I can write cloudy cool. I cannot use any other attributes. Yeah, I think yes, this is one example where no, these are examples where actually you will not get, because you are not able to express this expression. You know that you are not able to express this expression that in the Boolean expression where sunny and warm or cloudy and cool. You have to express this, na? Sunny and warm or cloudy or cool. Now, in a tuple, can you express that? That is the point. In your tuple for expression of hypothesis, is there any way you express these Boolean conditions? That is the question.
Don't care.
Yeah, if you use don't care, so that's what I mean. Only don't care is possible, but if you use don't care, suppose I use don't care, then no, I can use either W. I'm just or cool. Now, if I use don't care and W, then no, this negative, because there are negative examples also you should see. These negative examples, which means that cool and W will not be satisfied. So this negative example will be a contradiction. Okay. And if I use this this sunny and cool, right? Sorry, if I use cool, then of course this becomes a contradiction. So with respect to this training data set, we do not have any particular hypothesis here. So the assumption is that if there are multiple hypotheses, suppose you have both sunny worm and sunny, cloudy, then it is okay. So we'll come to that, but no, this is, I think this is one conditions we can understand, that there are certain Boolean expressions which you cannot do. Actually, what I wanted to say also, that I have already given one example. Suppose there are three literals, like in sky you have sunny, cool, and rainy, and in two of those literals, it is satisfying, and the other literal, it is not satisfying. I mean, just to give you example, suppose it is satisfying sunny, all tuple, whatever may be the condition, don't care state, then it is satisfying for cloudy, but it is not satisfying for rainy. That means this is a negative example. Suppose this is a negative example. Now, this is also a condition, because you know that when you are considering any generalization or any kind of hypothesis, as I mentioned, that either the literal is satisfied by one of them, or the literal should be satisfied by all of them. Now, if you're in your training examples for the same combinations, keeping all other combinations, they remain same, but you find that for some of the literals it is satisfying, and from some of the literals it is not satisfying, then you have these conditions. I think this is a specific case for that. So then you have this kind of problem, though your training example may be following the the process, whatever data you have, but your hypothesis space is limited. Hypothesis cannot express those kind of expressions, and that's why you won't get any hypothesis there. Okay, is it clear? So that is the point I want to stress here, that it may not exist at all. Any solution may not exist at all. That does not mean your training example is erroneous. But it's a limitation of the presentation of hypothesis. Is it clear? So this is what it is written. So satisfying all positive and negative examples may not be possible. So if you are satisfying all positive examples, for example, if you are not considering the negative examples, so if there is no negative example, so that may be one situation. If there is a situation like that, then things are simpler. But definitely you have to consider negative examples, and then you may find that there are cases where actually you are not getting any representation in the form of your hypothesis. So this is what sky condition could be rainy or cloudy, but not admitted in image. So this is what I wanted to stress. Right. So let me continue once again. That so what are the approaches? As I mentioned, that computationally it's a search problem over the hypothesis space, and your objective is that you would like to search that hypothesis which will match the training examples. But since there are many alternatives, so you may have to put some more additional criteria by which selecting the proper hypothesis. Now that problem is there throughout machine learning. You will see there are many solutions, and then you need to take one of them. So you have to use some prior knowledge, other assumptions to do that. Right? Anyway, so let us not bother about this at this point. So there could be two approaches. One is that since there are orders are there, ordering is there, so you may systemize your search by going through that ordering itself. If you have certain way of arranging them in some orders, so your search may be simpler, because you may search from most specific, and from there you can also find out which would be more general to that. Sorry. And other approach could be, of course, you can enumerate every possible hypothesis, which is not practical. Now, the choice of the hypothesis space reduces the number of hypotheses. So that we have already seen in the previous class itself. We discussed that why our hypothesis space has less number of elements than all possible hypotheses. So there is one algorithm that I'll be discussing first. Is there any question?
Sir, why are we interested in finding means one point in the you showed the map of the ordering of the hypothesis?
Because
so
why 1 point? Why not all points? Is that your question?
Yeah, no. I am telling that why are not we finding some disjunction type of things so that it
No,
can
that
fit
is
all?
your constraint, because you have simplified your problem. So I'm giving example. Now this may not be the representative of every kind of machine learning problems, but this is a typical scenario. In every problem you will find there are different forms, and some forms are more computable, and also your representation becomes here, as you see, efficient. I mean, it requires less. I mean, representation becomes simpler, isn't it?
Yes, sir.
I'm sorry. When you
But
are
sir,
giving that kind of six-tuple representation of hypothesis, that's a simple representation, and your searching becomes also simpler.
no, sir, I am not talking about six tuple. So we are finding an hypothesis like a point in the map such that it can fit all the training example. So
Right.
so why can't we make it more general till it accept, and if something remains, then we can add in disjunction some some other hypothesis.
Yeah. So your answer to that is that no, you are trying to make your problem more complex. You can do that, but then your solution approach would be different.
Okay, sir.
So you can always you can try to make a powerful representation or a very generic representation. Sometimes you will see that your representation becomes empirical also. So it doesn't matter. I mean, you have a very powerful representation which can consider all possible situations, but representation itself requires large amount of space, almost of exponential order of input to data set. For example, if I enumerate, if I have a kind of hypothesis where it would be simply lookup table kind of hypothesis. So you have always a lookup table, and that lookup table itself is your training example, isn't it? So we are trying to get a compact and precise, a compact representation, which is easier to compute, which takes less time, which takes less space. So these are all other considerations, and which tries to generalize more, the characteristics of the input data set. So there is certain order in the input data sets, and you are trying to impose those orders, and that's why to get a solutions according to that order, you are also putting some constraints in your hypothesis. So this example does not give you those flavors, but there are other kind of problem domain where you will find that yes, we try to simplify the representations or try to keep the requirement of space for representation of a particular model, try to keep it as simple as possible because of this only. It tries to capture more general pattern, generic pattern of the distribution. So there are concepts like overfitting, underfitting. We'll discuss those things later. So this FindS algorithm, what it does that it is actually trying to find out the more specific hypothesis. So in your space, it will try to find out that hypothesis or a set of hypotheses. Sometimes it may be, or a hypothesis which is an element of that set. There could be multiple comparable, non-comparable hypotheses, as you see in that ordering. But it would get one such hypothesis which will be more specific. That means any other hypotheses which are more general to it will not be selected only. So it is, in other way, it is saying the minimal general hypothesis. So what it does, it considers only positive examples, because the assumption is that it will satisfy only positive examples. So if it satisfies only positive examples, naturally, and also it will satisfy only those positive examples, and any other example which is not included, they are deemed to be negative. That means they should not be satisfied. So that's the constraint. That's the constraint for most specific hypotheses here. It is not a single. Once again, it may not be unique also, but it is with respect to that ordering. There is no other hypothesis which is more specific to it. So that's why it is not considering any negative examples, because only it is satisfying the positive examples, and any negative, any other examples which are not satisfied, it assumes they are all negative. Right? So what it does, so for each attribute constraint AI in H, so I'm just describing the algorithm. So before describing this algorithm, let me okay, the example is there. Let me just tell you the algorithm for the sake of time. So if the constant AI in H is satisfied by X, then do nothing. That means already you have an H where H and you have the you have an input X. So you have an input X. Sorry. And in X, it's also represented like a tuple. There is an attribute position where the value is AI. And suppose you have an hypothesis H. Now, with this input space, if you find that this constraint, so since it is it's a conjunctive form, you are checking every literal of you are forming every literal given this input, and then you are checking with respect to that Boolean expression with respect to that literal whether it is satisfied or not. So if it is not, if it is satisfied, then you don't have to do anything with respect to that attribute position. But suppose this position is not satisfied, then what you should do? Then your hypothesis needs to be modified, because in that case this Hx is definitely going to be 0. I mean going to be null. Sorry, going to be false. Is a Boolean expression and it's a conjunctive form. So what I should do then in that case, that I should make it satisfied. Now in that space already with some value, if the value it's a value, we don't start with a value of null. So which means in that space there are already some value for which it has been satisfied. So if it is satisfied, then what I should do, I should make it simply don't care, because that is the only allowable form for generalizations. I cannot take again disjunction of two attribute values put together as a combination. So that is the limitations, and that is the constraint on the formation of our hypothesis. So I will put this thing in this case. So in our training examples, with respect to this assumption, there should not be any kind of contradiction. That is what we have to see. And if there is any contradiction, then there is no solution. So when you get a positive example, so since you are dealing with positive examples, so you will not get any contradictions, and assuming only that negative examples. I mean, you are not allowing any negative examples. So the output, the hypothesis H. So this is how the H gets updated always. This always H gets updated. So whenever you have more than one value satisfied at a particular attribute positions, then actually you will have a don't care state there. And as you understand, you are starting with, of course, you can start with null, all null. Then for the first occurrence of attribute value, you have to just simply put that attribute value on it. So that I hope that you have understood. So with respect to an example, let me tell you, and this also you should note that we are not dealing with any negative example, because the form of our hypothesis is allowing positive values only those positive training examples. So in your target function, this is the limitation you have in your FindS algorithm. So that is a problem. Yeah. Something I have written there. Right. So these are the assumptions. There is a hypothesis H. Yes. Any question?
So, like in the last example, we considered sunny, warm, and cloudy, cool, right? So
Right.
there will be don't care in this FindS algorithm, right?
Yeah, sunny, warm, and cloudy, cool, because we are not handling negative examples, so all will be don't care.
Yeah. So both will be don't care, right?
Both will be don't care. Yes. Okay, so we are not going to check the other things. So that's why those are the assumptions. So there's no contradiction in the negative examples. And there is a hypothesis H in describing target function. These are the assumptions. So here we are not really checking whether there exists a contradictions, whether the hypothesis is really empty. You will always get an hypothesis with respect to these assumptions. And there are no errors in training examples. This error is relative with respect to this definition now. If there is any contradiction, we assume there is an error. Everything except the positive examples is negative. So that is the condition of the hypothesis that you are selecting. Right. So example with respect to your input data set. So you see that you have started with most specific hypothesis, which is given by all null, right? H naught, that is all null. And then you take the first training example in your data set, say sunny, warm, normal, strong, warm, same, right? So what should be your H1 in that case? Can anyone tell me?
X1.
Same as X1.
Same as X1.
So H1 also it would be represented the same way, but no, meaning is different. You understand the meaning is different. It means that sky equals sunny and temp equals warm and etc. etc. I hope you understood, right? When you read the input is that the value of sky is sunny, something like that. In that way you are, but they are all Boolean literals. So H1 also is represented in the same form, same representation with respect to that input. Now let us consider the next example, X2. Sunny, warm, high, strong, warm, same, positive. That means it's also a positive example. Now you have to consider. So for which value or for which value of attribute position, I will talk about attribute position. It is not satisfying. H1 is not satisfying. Can you identify?
It is the normal and high.
Normal and
Yeah,
high.
the third position, right? In the third position. So what should we do? What should be then H2?
Don't care.
Change it to
Don't care on third position.
Yeah, sunny, warm, don't care, strong, warm, same.
Don't care.
Okay. Let us take the next example. So it is rainy, cold, high, strong, warm, change, and the level is negative. So what should we do?
Ignore X3.
Don't do anything, isn't it? So what should be H3? With respect to, if I say that every input sample and then the next hypothesis so you'll be considering, what should be H3?
Same as X2.
Same as H2. Exactly. Right. Let us consider the fourth training example. Sunny, warm, high, strong, cool, change, and you have the positive. It is a positive example. So what should be the why does it why it is not satisfying the H3? Because H3 is your current hypothesis. You have to always evaluate your current.
Last two
Fifth
positions.
position is a change. Warm.
Last two positions are not satisfying. Huh?
Yes.
So H3 needs to be modified, and you have to make them don't care. Is it clear?
Yes. Sir.
Right. So I think today this will be my last slide because I have already passed almost 8:55. But what are the problems? As you see, it throws away negative examples and can't tell whether it has learned the concept in the sense that you are really very much restricting yourselves to only satisfying the positive examples. So in that way, it is, I should say, it is a bit biased. And can tell when training data is inconsistent also, that is not possible. No, since you are throwing away, whether there is an inconsistency with respect to your assumption, version space is null, that you cannot find out. So these are certain problems, and which we will see that there are techniques to deal with these problems in our next classes. So, but these are the advantages, simple, outcome independent of order of examples. We can see that, we can think about it. Now, this is the alternative, keep all consistent hypothesis, and that's what we'll be discussing in next lectures. What other algorithms are there? One algorithm is candidate elimination, which is exhaustive and which is not very practical, but there are other algorithms. So let me once again stop here and let me take your attendance first.
Sir, I have a question.
Okay, I hope it is downloaded. So, do you have any questions?
Sir?
Yeah.
So in the last class, in one problem, in one counting problem, you had counted the all null set only once, like
Right.
the null in any one attribute and all attributes, they are counted only once.
Right.
So I wanted to ask that are they all same, or the output is same, that's why we are counting it once?
Yeah, because they are equivalent. They are equivalently the same target functions, because whatever may be the value, if I consider a target function's final representation of target function is a truth table, they have the same truth table.
Okay, sir.
Okay, so I hope that's all. And then thank you very much. Again, we'll meet next week, Wednesday.
Sir,
Bye. Yeah, any question?
excuse me. Hello.
Yeah.
Yes, sir. Sir, in the first lecture, you mentioned that we have to make a weekly notes, like
Yeah,
we'll
we'll
have
be
to
uploading. We'll be uploading today itself, and you have to submit by Sunday.
it will be in the Moodle, right, or a Google
It will
form?
be in the Moodle. It will be in the Moodle as an assignment. It will be in the
Okay.
Moodle as an assignment.
Sir, could you please upload the PPTs?
No, PPT I told already. At the end of this lecture topic, then only PPT. Please get a book. Okay. Okay, fine. Thanks.